This was the amplitude I was telling you to calculate. And did somebody try? Did somebody succeeded to do it? Okay. We said there is a G Newton, okay, you could agree with this. We have to remember that the dimension of G Newtons is 1 over n Planck square e to the minus 2. We can understand later why you have to put G Newton with dimensions, okay? So now we're talking about helicity that are higher, okay? And remember the spinors under this transformation transform as spinors, okay? It's like a spin a half, okay? So it's minus a half theta 1, okay? You get back, you got, for the particle 1 has helicity minus 2, you have to put many of them, as you can imagine, okay? Because you want this, when you do this transformation, to get e to the minus the helicity of this guy. Okay, so what you were saying? Okay, this guy have to appear 4 times, and we have to contract with somebody else 4 times. Because if we have 4 times, you multiply by 4 and you get minus 2, the helicity of the particle. This is the rule, okay? To have the right phase, okay, under this little group, it has to get to the e to the minus the helicity of the particle. So to get minus 2, you need 4 of them. 4 times a half give you 2. Okay, but here we have to put somebody. If we put 2, okay, yeah, of course the 2 can transform in the same, it's a spinor, e minus a half theta 2. 4 of them give me minus 2. Okay, so I have these guys already done, okay? This transform properly to reproduce the helicity of these guys, this transformation, okay? And now I have to go with the same, but plus plus, okay? This seems to be easy. It will be 3, 4, the 4, okay? Okay, because the 3, this guy is transforming the opposite way. It's a positive phase. And the same for the 4. Four of them give me plus 2. That is the helicity that we chose. We are looking for the amplitudes with these helicities. And now you can try the other ones, different helicities, and try to get it. Okay, but let me finish this one, because we are having many dimensions here now. You see, the higher the spin, this is the point, the higher the spin, more of these spinors I have to put to get the right helicities, okay, the right behavior of this amplitude under the transformation of the little group, okay? And now I have to put more things in the denominators, okay? These guys have dimension 1, so 4 times, this is 4, plus 4, 8, dimension 8. Okay, 2 dimensions are killed by G Newton, 4 minus 2, 6. Okay, I have to put something of dimension 6 down here. Remember what I have at hand. I don't want to put more spinors. We will change my rules, these rules. Okay, so I cannot put a 3, 2 here. Okay, we'll change completely the rules that already fixed. I have the proper rules that when I do this transformation, I get the helicity into the theta times the helicity of the particle. But I still have the other variables STU. Okay, now it's clear, because you cannot put double poles or triple poles. I cannot put S cubed. Okay, so that's it. I can have 2S, T, and U. No options. You could also guess, because of course I have some crossing symmetry. Okay, these are boson the gravitons. You can interchange them, and this beautifully has crossing symmetry. If I interchange 1 and 2, this is invariant. Okay, so that's it. Okay, hours of calculation through Feynman rules can be derived in a simple way. The only thing you have to remember is these things. Okay, if you don't understand very well, okay, it's something to understand. Once you have it, you can write it like this, and that's, this is why Brando, when he was telling you about amplitude related with gravity, automatically went to spinors, because otherwise it's really crazy to give you something. Now there is something more to check. Okay, this is the first check, and we see that this amplitude has 3 poles. The pole, okay, when S goes to 0, it blows up. When T goes to 0, it blows up. When U goes to 0, it blows up. Okay, so you have 3 things to check, okay, if it factorizes. Okay, when S goes to 0, we say this has to factorize into amplitudes. Okay, this has to be something mediating A. Okay, something like, okay, when S goes to 0, this has to be something like, looks like Feynman diagrams, of course, because you have the intuition, but what the only thing I'm saying, this is a 3-point amplitude, okay, where I have to have something mediating here that is a graviton, a particle. They give me the pole, okay, 1 over T, 1 over S, sorry, and another 3-point amplitude, okay? And now you could go back, because we started with the 4PT here, the 4 like amplitude, 4-point amplitude, same. But of course, we could have calculated, we could have looked at this. The gravitons, 3-point amplitude, you could see that there is 1 to write. In fact, it's very simple to write, because what is the difference between a graviton and a photon? Well, the only difference is that the helicity of a photon is +1, -1, the helicity of a graviton is +2, -2. This is not much difference from this point of view, okay? From the point of view of fields, it's really a mess. It has to have 2 indices, contracted, coupled to the T mu nu, all this thing. Here is just twice it, okay? So in fact, I can use the one that I had for the photons. Well, not photons, because we show had to be antisymmetric, so had to be different. So for the gauge bosons, spin 1 object, there was this one, and square it, okay? And just square it. This had the properties too for when the spin 1 particles had -1 +1 -2. Now is putting a 2, okay? If you square, they will have the right properties, transforming by this one here. You can check it, okay? You can check it. And now the fact that, be careful, because we had dimensions, okay? We had also, the dimensionality had to be okay. This has dimension of energy 1, and this has already, for the gauge boson, dimension 1. So square has to dimension 2, okay? So you see, the only one I can write with the graviton has dimension 2. I cannot write anything else. And this is why we have to put a coupling that has dimensions. Square root, we call it the square root of G Newton. Okay, so we learn why gravity have to couple with something that goes with energy 1 over, we call it 1 over m Planck. Okay, a strength that has 1 over energy is to -1. Okay, dimensionality of this guy is energy -1. It's the only way we can do it. Okay, it's the only way we can do it. And now you can check, you have to check, I leave it, I will not do it, that indeed when S goes to 0, this factorizing those 2 guys, that are these guys, okay? You can just take it, for example, this guy, put it here, and then try to see that really is exactly this when S goes to 0. And similarly for the T channel, okay, you have 3 checks to do. Also, the T channel, factorize into these guys that are this guy. There is only this guy. You can check there is no more plus, there is no plus, plus, plus. Okay, relatively very simple gravity. And there is also a U channel. Okay. So 3 checks you have, okay, 3 checks. Because as soon as you fix it here, this square root of G Newton will come here, Okay, this cannot be different from that, because this comes from 2 times this guy, square root of g Newton, square give me g Newton, okay? So you fix here, you don't know what is this. Let's say I don't know about gravity, I have a cap, okay? I know this amplitude has to go like this, times a coupling that has now, I'm forced to have dimension 1 over energy. I don't know what it is, but now when I go for scattering of gravitons, I see it goes with this g Newton, okay? So there's 3 checks, and it works. If it would not work, we would not have theory of a spin 2. Okay? Now, okay, so this exercise you can do, and now you can ask yourself, what happened? Looks like it's easy to build up theories of spin 3, spin 4, okay? Okay, spin 3. Let me just do it if you want. I put, okay. Put a 3 here. Helicity is -3, +3, -3. Okay, let me call it h hat just to not be confused with the other. And now I know it will work if I put a 3 here. And of course, this has to have different dimensions. But what happens when I go here? Okay. When I go here, this is going to increase. Okay, you can already guess because I need more of these spinors. Okay. Need more. I have to go to 6. 4, sorry, I had 4 here, so I have to go to 2 more. Increase by 1 unity. 6. Have this g Newton. That is not the g Newton. Use g Newton with different powers of energy, -2, -4, I think. No, we can see here because this has dimension of 1 to the 3, 3. So this has to have dimension of -2, so squaring -4. So 12 -4, 8. Have to put something with dimension 8 here. Okay? Just dimensional analysis. But I only have these 3 guys, and I cannot put 2 times S because we'll be double pole. Okay? So I can put S, T, U, but it's still missing somebody with the. Cannot put again no U. I'll have a double pole. I cannot put T. Okay? So this missing guy here to give me the right dimensionalities that tell me I cannot do it. Okay? I got to spin 2, finish. I cannot go on. This is why theories, okay, thinking now here, spin 3. Okay? Trying to go up because it looks like simple when you see the rules. Okay? Okay, there is nobody here because there are only 3 Mandelstam variables in the 2-2 process. Okay? So this is why we cannot build theories of higher spin. We were lucky with the spin 2, it worked, everything worked. We cannot go spin 3, spin 4, spin 5. Finish. Okay? I cannot have massless. Very good, thank you to remind me because we always assume masslessness here. All particles are massless. Of course, I can put mass, and of course, I can write a theory of a spin 2. And already Brando was telling you these theories, be careful because as soon as you go high energy above the mass, you're going to have problems. Okay? And with the discussion he was talking, okay? So there is another problem with when you put mass. This theory has little range of validity. Okay? But that's another story. Okay? Massless particles can only be 0, half, 1, 2, and I'm missing 1 guy. Okay, we say 0, at least spin 0. We have constructed this, and this, but there is a missing guy in this. Who's missing? 3 halves here, okay? Now you can do it. You can try it. to write a theory spin 3 halves. And it will be possible. It's also a possibility. You can do it, okay? You can just try, starting with this is a very simple way to build up supersymmetry. This will give you supersymmetry, okay? You will see you'll have to have conditions for your, when you look at your poles and factorization that require symmetries, what we call supersymmetry, okay? So this possibility is still there. It's very simple from the amplitude methods, complicated from the other, but here is just as you said, as you were seeing here, okay? I have to have the right rules to reproduce the right transformation of this thing under the little group and give me, for the particle one, the polarization of the particle one, when I do the little group transformation. Okay, so first 3 halves can be done, okay? And in fact, you could guess it, okay? You could try to do it, okay? You could try this with 3 halves and see what it comes here, okay? In fact, I was thinking the other day, I could have started, instead of the way I started, I was thinking, this is something your grandmother could do, okay? But the only problem your grandmother could be not understanding is this thing, because I don't know, this thing, a little group, whatever. But understand that you're writing things like this, okay? And I can write another one, it has to have dimension 1. Grandmother, I think, knows about dimensions, okay? So this dimension 1. I can have this also by divided by 2, 3, will tell you. And I can have, this is easy. I can have also, I don't know, 1, 2, also 3 here. I have to put 2, 3 here, okay? This has dimension 1, and so on. Why not? Okay? Potentially are decoupling. Now you have to recognize that these are 3 couplings. Okay, now you have to do the little group things to recognize what is this interaction. It involves 3 particles with 3 helicities. This involves 3 particles with 3 helicities, and anything you want to invent, it will involve particles with 3 helicities. And you will, some of them will see that they are not okay because will involve particles with probably spin 3. Okay, helicity plus 3, minus 3. Okay, but a priori this is allowed. Okay, this is potentially couplings, 3-point amplitudes. Okay, and good to see if there were more. You see, we are not taking the Lagrangian path. The Lagrangian path already is limited here. It looks like could be more. And unfortunately, we are not getting much more, okay, because we don't see how to go beyond this thing. We already knew how to do it with fields, quantum field theories, okay? But I'm saying this is a wild game that you can go, okay? Write things and write a thing, I don't know. You see, I put here 10 and I put 9 here. Why not? This has dimension 1. Of course, you will see this guy with a lot of helicity involving in this 3 vertex will be some guy with high helicity. And we already see that we go to build up. This is a not physical thing. There would be 3-point amplitudes, of course, out of them, because when you go to the physical real momenta, they go to 0. Okay, because there is no invariant, Lorentz invariant can be done by, as we said, there is no STU equivalent in 3-point amplitude. All of them are 0, all the invariants are 0. So you want to go to 4-point amplitude, and when you go with this interaction to 4-point amplitude, you will see it's not. Some of them, of course, will be the theories that I already gave it to you, the standard model. You will discover some of them involving the 3 halves. Okay, you will get it from these things. And some of them will involve higher spin that you cannot do a realistic theory. Okay, but you see, it's very easy to build up the interactions, okay? You don't need going through okay, only this part, the little group part that is just to motivate you that there is something, if it was confusing to you, probably to go back and it takes 10 minutes probably to sit down and get it right, okay? Yeah, this one, yeah. But the 3-point amplitude, you see, is not really physical because we went to the complex plane. We built it, but now we want to go to the real thing. Our 4-point amplitude is the first thing, real thing that you can see. The scattering of 2 of these particles, the scattering of these particles with somebody else. Spin 3 scattering, you can also write a spin 3 with a spin 1. You tell me and you do it, and we can do it, okay? It's when you go to 2 to 2, and now you want you see automatically, you see, wow, I'm not going to make it here. Okay, I'm not going to make it. Here is very simple. Very simple, much more complicated if you go do it in fields. Of course, you can also see that how you do it in fields. We know that when we have spin 3, we have to couple to some conserved current and have 3 indices. And it's the famous theorem that there is such a thing doesn't exist. So we cannot, the theorem goes in a different way to prove that there is no possibility to do more higher spin because we don't have more conserved currents, more conserved tensors to couple to it, okay? Question? Now, there is a very interesting method to, so we limit ourselves to 4, like amplitude, 4-point amplitude, but, and in the case, it's relatively simple. You just can guess the answer as we were doing. Dimensional analysis, proper transformation under this little group, okay, and not double poles, factorization, okay. If you want to go now, you tell me how I'm interested in 3 gravitons going to 3 gravitons, so 20 gravitons going to 20 gravitons. Things are not so easy to guess as you can imagine. Factorization is not so easy to guess. But there was an amazing paper that I don't have time to go through it, okay, so. Okay, there are some relations, there is a recursion limit, recursion method, okay, that is called, very famous, you can find it in already in the Wikipedia, it's called the BCF-W method. Okay, that tell you how to get higher point amplitude from lower point amplitude. Okay, so you start building the 3, the 4, 5, 6, 7, okay, and it's a systematic way of getting it. It's a very nice paper, it's an amazing paper that tells you how to get higher point from lower point. Everything on shell, okay? 3 level, of course. Okay, this is this, okay, this beacon from Brito. The C from Cachasso. Feng Witten. A very interesting method that you get into, yeah, I mean, it would take me probably 2 lectures, 2 hours to get it into it, okay? Now, for higher point, of course, probably most of us, we are not interested in 20 gravitons scattering with 20 gravitons, okay? And for 4-point amplitudes, I don't think you need that. I think most of them, at least when I have had to work for these things, always I did it like this, okay? I guess the answer by dimensional analysis, I see factorization, and it's much easier than the other case. But the good thing of this is a systematic way of always doing, okay? Of always calculating it any point. Amplitude as a function of the lower. So you have to, the good thing of the amplitude method is you build up, okay? You start calculating 3, you go to 4, 5, 6, everything is good to keep it. You see, it's slightly different from when you do Feynman rules, okay? Feynman rules, you have to draw a diagram, and now every time you calculate, you almost start from the beginning. You don't use something, oh, I calculate already this amplitude, can I use it? No. You start with you draw your Feynman diagram, start it again. You do 2 loop, you have to do again from the scratch. I cannot use my 1 loop, no. 2 loop is completely different. Here not. Amplitude method is you build up, okay? There should be a library of these things where I check the previous calculations, okay? Because as soon as you have this, 4, now you go to 5, okay? Because 5 will have something like this here, okay? So I'll have to ask for factorization, cut here, and I have to say this, okay? When I go to 1, 2, 3, 4, 5 gravitons, for example, okay? Will be an amplitude look like this, and I will, when I demand for factorization, I mean, I will go when the kinematics variable blows up at some point here, and we'll have to factorize in this 3 point and this, okay? But I already, you see, I need the 4. You need the 4 to plug with these 3 and see factorization works. Okay? So I keep the 4, don't throw anything, everything recycle. Okay, and I go to 6, I will need the 5. When I go to 7, the 6. Okay? So that's a good method, okay, because as soon as you pile up your things, you keep them and you will use it later. And when you go to 2 loops, also, 1 loop will be important. Okay? Okay. Now, there is another thing. Okay, so I close the chapter of gravity. I don't know if somebody is interested in other things. Sorry, new structures can? No. Okay, so you mean, you see, I don't know if exactly I understand your question. Are you asking if I will need new structures? What do you mean? New couplings?
Yes, which is not factorizable in terms of your point.
No, you will not need, for example, for gravity, if you don't introduce a new parameters, now we will do it. Because when we do effective field theory, it is the cutoff. Okay, the famous cutoff lambda, which we expand over. Okay, we do momentum over cutoff. If we use lambda, it's a new dimension parameter. And now I can use it to put it, because down here, because we are expanding, it has to be in the denominator. And put it here. Yeah, if I use it, yeah, and the square, you see. So when we go to effective field theory higher up, yes, we will find this. Now, if we are at the leading order, the lowest order, no. Okay, I'm not saying, right now I don't use it. Okay, I'm doing expansion, I want to calculate things at lambda, order lambda 0, no lambdas. So I don't get anything, okay, anything else. One coupling, fix everything. G Newton, fix everything. Exactly. Now I can couple these 2 matter. Okay, exercise, you do graviton, okay, go back to the graviton spin 2, and you couple to spin 2 minus 2, you couple to matter, yes. Okay, and now you do the calculation, and yes. And you say, well, why I should put G Newton here? I can put a square root of G Newton. I can put another G Newton prime? No. Okay, why G Newton is universal? Because when you do factorization, exactly, you will see that you need to be, as we said the other day. Okay, we need the same coupling, we need the same G Newton. Okay, otherwise we'll not factorize properly. Okay. So in a sense, this is the point, that you have different channels, all of them, all couplings here have to reproduce the one you have here. Okay. The square has to be that guy. Okay. So this is how the universality of couplings or here of G Newton appears, okay, by the proper factorization of anything you can do. But it's very easy. Gravity coupled to fermion, gravity coupled to gauge boson, to, I don't know, any guys of these guys you can use. Okay. Okay. Now, if nothing else, let me go back to the standard model, because there is some property that I want to mention that is, that's a kind of surprising, it's not clear why, but if you try to look for, so back in the standard model, but this is valid, back to the standard model, but this is valid for any theory like this ones. Okay, if you calculate, I don't know, amplitudes, okay, that contains minus, elicities all minus, like this one or this one. Okay. All give you 0. Okay. In fact, you can show that all standard model for PT amplitudes, for PT have the total helicities. When you sum the helicity of the particles, for example, here, minus a half, minus a half, minus a half, minus 1, minus 1, minus 1, minus 1, I sum the helicity of all the particles involved, and the total 0. Except, so it's not a rule, there's an exception, only one exception. Otherwise, you would say, well, there must be a theorem here. This is a mystery. I don't know. I don't have any reason why this happened. In fact, we have an exception, so it's not a theorem. Okay? You calculate things. You sum the helicity, it has to be 0. Okay? Here is the example we were doing before. It was also plus, plus, minus, minus. I mean, for the graviton case that we had before. Okay, we got a non-zero result, but because we had plus here, plus 2, minus 2, minus 2. Okay, you sum all the helicities, okay, and you won't get 0. No. You find it when you do it in helicities. You don't see this structure. You see, this is something important. Standard model, this thing is 0. You can prove it in other ways. Of course, there is many, because this is well known already happening in gravity. It's already known in Yang-Mills theory. It's also happening in the standard model when you put fermions. Scalars, of course, has no helicity, and plane is raw. But you can argue about the reason of that using supersymmetry. I'll say, what has to do with supersymmetry? It's a trick. It's a trick to show these things. Okay? So you can show in different ways, but there is no, to my knowledge, there is not a deep principle why these things happen. Also, because there is an exception. Now I tell you what is the exception. But this is a surprising thing, and it's very important. Okay, because if you want to do physics, okay, you see, it's telling you that you do, I don't know, scattering, where you have definite helicities, you get zeros in the standard model. Okay, and now we'll go beyond the standard model. I mean, higher dimension operators, the equivalent of next term in the expansion in effective field theory, and we'll see that these properties disappear. So it's a strange property, okay, at order lambda 0. Okay, we define the standard model at order lambda 0 in my cutoff expansion. Okay, let me talk about the exception. Okay, the exception comes from, there's only one, comes from taking this tree level. Remember, we are doing it right now tree level. Okay, when I put it like this, it's tree level. Everything's tree level. It comes surprisingly from this type of diagram. Okay, let me see if I see it. Higgs, dagger going in that direction, Higgs. Okay, I can put this is the doublet Q, I, Qj going to down. Okay, this is what we call the left. I don't know if I put it, okay, let me put it in fields because you will recognize the quantum numbers. This is what we call the down right. Okay, I put it like this, just to recognize the quantum numbers of these guys. Okay, so is the guy that is proportional to the Yukawa coupling of the down quark times the Yukawa coupling of the, sorry, here is up, here is down. Okay, now you can have minus, 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 minus. Okay. Total helicity minus a half, minus a half, minus a half 4 times is minus 2. Of course, sorry, I didn't say it, but of course, every time we have angle brackets, I can do it the same with square brackets. Okay, so it's a trivial change of all the helicities. Okay, so everything can be done square, everything in angle brackets, I can go to square bracket and I change the helicities everywhere. Okay, so everything I say here, you can have minus, minus, you can also have with plus, 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 and plus, okay? But changing all the helicities, okay? So it's a surprising thing because it's proportional, as you can see here, to lambda up, lambda y up, y down. Okay, so things that we have up and down, you can do it. In fact, you know very well the standard model, you know that you have a similar diagram here with you replace, you can put the leptons, okay? So, also by U right going to the E right and Q going to the left-handed, okay? And in this case, the amplitude is proportional to E up Y electron, okay? Since down quark, so here the up can be the top, the coupling is large, but we have to multiply also by the down, okay? The highest Yukawa of the down type quarks is the bottom, but it's still smaller, okay? Bottom is 5, the mass is 5, so it's 5 over 100 more or less, so it's a small Yukawa coupling, okay? So this exception is a small amplitude, okay? Because carries, okay, this can be the top, but carries the bottom, okay? And of course for the down is negligible, for the strange also is negligible, okay? This is a mystery, okay? But will be important for later when I say, when I talk about the loops, okay? When I talk about loops, these properties will be very important. These properties here will be very important, but it's already important for phenomenology because I said, tells me how, for example, okay, let me probably discuss at the end, okay? Let me go on, I'll discuss at the end. Why it's important, because the effect of interference, okay? I have a couple of things, one thing more, and after that we go for next order in the expansion, okay? But I will flash you the results, okay? Now, it was already asked this question, okay, that can take 4 Higgs, okay? And you will ask, what can I do with this? Because helicity is 0. I don't have the power of the spinors. I don't have any constraint coming from to transform properly, okay? Because this is important because I have to reproduce the proper helicity, but the helicity is 0. I don't have anything there to put in the numerator, okay? And because it's a 4-point function, it is dimensionless, okay? So there's nothing to put, a constant. We call it lambda, okay? So there are also, it could happen, and this has happened, that there are 4-point functions that are not determined, they don't have singularities, okay? They don't get any singularity, okay? So are not fixed, the coefficient in front are not fixed as a function of the 3pt, okay? Remember, singularity tells me factorization, and now, bam, this guy has to be according to this guy, okay? So I cannot put another parameter, so I put, but here, yes, I don't know what it is, so I put lambda, okay? So you have to know that there is, okay, extra parameter in your theory, okay, as we know in the standard model, okay? But this is how appears this thing, okay? Of course, can be other contribution that has singularities. And those, yes, will be determined. For example, those coming from change of a W, standard model, those will give you singularities. So I can build something with singularities, something I can easily guess what is the answer. You will have to have, I don't have polarizations, I don't have, spinors, so we'll have to be made of ST and U. Okay, so this I don't remember if it's T square over SU or U square over TU, okay, I don't remember depending, because you have a crossing here, symmetry. Okay, depending how we cross, I think this is probably, okay, I have to understand. Okay, so you can build, okay, something with STU that is dimensionless, okay, because we're talking about 4PT is dimensionless. But those are fixed because I will demand factorization, and I fix already this to be G, okay, so this is something I can calculate it, but it's fixed, not new parameters. It's important to know your parameters because it's your ignorance, okay, of course. There is an ignorance, something the experimentalists have to tell me. And already Rodrigo told you when we go to loops, these parameters will be important to renormalize the theory, okay? Some parameters, as in the case of quantum field theory, you use them to eat the divergences, okay? The same we'll do here, okay? These are the parameters we will eat the divergences when it appears at a loop, okay? And everything will be consistent by this process in the same way as consistent in quantum field theory. And now this amplitude with no parameter can appear in higher point amplitudes, okay? So in some sense, a new building block, okay, that will appear in other things, okay? If there is no question, I'll move to go beyond that. Sorry, tell me. What vertex? For gluons. Okay. First, can you, okay, in the same way, okay, in the first same way, you fix the helicities. Okay, you have to tell me what are the helicities. All are possible, plus, minus, minus, all are possible in principle, all are possible. Later on, you realize, no, only when they sum total 0, you get something non-zero, okay? You later on, okay, so this is nothing I can, of course I can prove it to you, this is the case, but it's not something I can tell you in a few minutes. The proof to me are long, proof are long, okay? The only thing I'm saying, there is no, I don't know if there's something deep, okay, here, I don't know. Look, it's a good thing to think about it, okay? I don't know, every time I look at this, it looks like yes. But of course, I have an exception, so it's not something too deep that, okay, but there's an exception, but the exception is things that the standard model has many couplings, okay, as I said, you need ups and downs, or ups and electrons, okay? Otherwise, you will not have it, okay? And you have it only for -2, okay? Not -1. Okay, for example, only this guy. It's good when you have a rule up to exceptions, okay? Of course, if the rule is fulfilled, completely perfect, but if the rule is fulfilled by a little example, I mean, by a little exception, it's still good to know the rule, okay? So you have to fix it here with gluons minus plus plus, is the only one will be non-zero, and you will do it in the same way, okay? The problem with the gluons is that you have flavor, A, B, C, D. Another good question that you can ask here, can I put more gravitons? You see, these are the good questions that you never understand well when you do quantum physics. Why one graviton? Can I put 2 gravitons? Can I have a graviton charge under some group? Can I have non-abelian gravity? No, okay? No, you can start trying to do it. No, will not factorize, you will have problems, okay? All these theories, anything you think, you can test it by doing this process, okay? So now the problem here is that you need flavor to have interaction, okay? If you only have gluons, if you only have photons, you don't have this process. You need flavor, and now okay, it has to factorize, okay? You write the spinors, but now you have also to be careful with the flavor indices, okay? It's relatively simple. If you want, we can do it. Some break or not, we spend, of course, I mean, I've done it many times, okay? There is a beautiful thing to relate this with gravity that is called the double copy, that tells you how to go from this one to the gravity one. I already told you here how to get it from a spinor, you square it, okay? This is squaring. Gravity is like a square of Young-Mills, okay? This you have heard many times. Here is very clear. Not so clear when you do Lagrangians, but here is clear. I had this or gauge, and I put a square to get that one, okay? Because the least CT is twice the one of the photon, okay? Here, similar, it's a little bit more complicated because when you talk about 2-2, you have flavor, but you can go from this one to the graviton by what is called you interchange kinematics with tensor invariance under the flavor. It's a strange, it's a double copy, it's a strange permutation you do, and it works. You go from Young-Mills to gravity and back by this permutation. A strange permutation, you interchange, you see kinematics, variables, okay, like momentum, with some group factor, FABC, okay, copy. Okay, so it's something a little bit weird, but if you do, it works, okay? This is why people get a lot. I mean, this helps a lot of people to get into calculation of the gravitational wave. You know, these things are used for this day calculating orders, next order on the I don't know, the merger of black holes. Okay, do it through these methods, and it helped a lot that people had done a lot of calculation in giant mills, and they could recycle easily into gravity by this permutation. Because here it looks like gravity is not a big pain. It's a big pain in Lagrangian. So you do it in Lagrangian, it's not a big pain. Okay? As soon as you have one, you have two, three. Well, three doesn't work, but it's easy to get it. Okay, I want to flash it. Okay, let me flash it because you can do it by yourself. Okay, you calculate the higher dimension operators in the standard model. You say, well, we calculate it, okay? Standard model is just order lambda 0. Okay, in quantum field theory, now when you go to 1 over lambda, okay, now you have to calculate how many operators you have that, how you have there, no? Okay, remember we're doing the same thing, okay? So now we're looking for amplitude that scales at 1 over lambda, okay? And now you can spend a little time, but you will see that the only one I can do is this one, 1 or 2 over lambda. That is a 4pt. Involving two scalars and two fermionicity minus. Has to be dimensionless, okay? The 1, 2 was dimension full, so divided by lambda, dimensionless, and I can do it. And this order is relatively easy to see that there is. What else I can do? Somebody has an idea? Okay, I don't put the flavor, okay, because of the Higgs are doublets, the fermions are doublets or triplets, whatever, okay, that can be put it, okay, just for simplicity. And of course, this is related with also, I mean, I have one here, so we'll have to put this is equal to some coupling here, see, some coefficient, that already Rodrigo was talking, some usually called Wilson coefficient, but this is just another coupling that they have to put. Okay, because I know this is proportional to this, but the proportional coupling, what it is, I don't know. A new parameter into my theory. Okay, experimentalists have to tell me. Okay, and this is one-to-one correspondence with something that you really know in field theory, that is what is called the Weinberg operator. It's not so easy to get when you do fields, but if you go through all possibilities, when you do fields, you see in the standard model is only one dimension 5 operator. This is the famous one when the Higgs zeta Beth give mass to the neutrinos. Okay. Now you see minus minus. This is why I was saying it's important that you don't get an amplitude. The total lambda total of this amplitude is -1. It was -1/2, these are fermions, -1. You see, as soon as we go above the leading order, we start seeing, yes, that rule is a surprising thing. Okay, I don't know. I don't know. You really don't know what to say. Okay, it's like standard model is so constrained by Lorentz invariants that they cannot make it. Now you can go to order lambda square. Say there is no more at that order, and you know it from field theory. There's only a famous one, and now you get 3 PTs. Okay, the only one you get now. You have to do it, but you can go. If you order yourself, okay, you sit down and you order yourself, you will see it's easy, relatively easy to get it. And now you have minus, 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 again, also 3 gluons, okay, because you can do 1, 2, 2, 3, 3, 1, divided by lambda square. 3 dimension divided by lambda 2, I have the lambda now too, so opens the more possibilities. Okay, and that's the only one, 3pt. Again, try to see if there are more. Simple. I have to take this, okay? It's a 3PT, I can only take, of course, the equivalent, okay, remember, okay, for any, okay, always, I can go for, I get another one by interchanging all angles by the brackets, okay? So I always have, I don't talk about the other one that is trivial to generate, plus, 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 where I change all these things, angles by brackets, okay? But I don't get plus, plus, minus here. The one I had in the standard model, I cannot get it to dimension 6. So there's a difference between dimension 4 and dimension 6 you're seeing now by the elicities. Okay? In one case I was plus, plus, always plus, plus, minus. Here is always plus, 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 or minus, minus, minus. Elicity changed completely at this point, okay? I go for the 4 PTs. Okay, I get a lot of them with lambda total minus 2. Before I had only that one. Okay, let me show it. What are these guys? So I put it here, ABC, because these guys are antisymmetric. Again, I cannot have a photon here, or a Z, or only one guy. I have to have several guys. Okay, so in some sense here, there should be something antisymmetric. Happened already in the standard model, this property. And by the way, this is related when you do operators with the F to the cube operator. There is a, we mentioned 6F cube operator. This is one-to-one correspondence. Well, yes. Okay, now I can have this also to boson with minus 3, 4. Okay, that is proportional to 1, 2 square on the square. I can have one, two, minus. Yeah, dimension 6 likes minus, everybody minus, okay, but not completely, but 1, 2, 1, 3, lambda square, and you can check it that you can have also minus, 1, 2, 3, 4, but you have 2 of them. You can write it like a 1, 2, 3, 4 lambda square, or you have another one that is 1, 3. Personally, I have done many things with operators. As Rodrigo was saying, I was also calculating all these anomalous dimension 6 operator in the standard model, all these things. Already to get the basis of operators, eliminated redundancies, took more time than doing this. When I get here, okay, let me see how many independent new amplitudes I get. In front of each, I have to put a coupling. I know how the spinors go, but I don't know the coupling in front, okay? Now there is also lambda with lambda total 0, okay? That are like 4 Higgs. You can have 1, 2. Have 2 of them. Okay, I'm going to complete, okay? We'll finish with this, okay? Minus, 1, 2, 3, 4. 1, 2. If I get something wrong, you can tell me. There are 1, 5 PT, I am almost there. There are several of them, but not so many. If you go systematically, you get all of them in less than a half an hour. Okay, this is 1, 2, 3, 4, 5. Okay, see, it's the first time you put a 5 PT that has no singularities. a very simple one. Is 1, 2 divided by lambda squared. Remember that this 5pt has dimension. The amplitude has to have dimension 1 over energy. Okay, this is the right one. And finally, I have even a 6pt. As you can imagine, because you have been discussing this today, I mean, the last days by Rodrigo, that is the 4-6. That 6 Higgs has no helicity, so only constant, 1 over lambda squared. The amplitude, 6pt amplitude has energy 1 over energy squared. Okay, so this is it. The only thing I can have constant. I didn't put constant in front of each because I only know this is proportional to this. Okay, and these are my new couplings I introduce when I do effective field theory. I assume that lambda is going to be larger than the energies. Here are energy at some point. Okay, so these are a small deviation with respect to the standard model. Okay, but are new parameters that I have to measure. Okay, coefficient in front. Okay, this is the idea of effective field theory. I think I have 1 minute or a few minutes only to comment now is, you see, total change I have of helicity, and it's important because when we calculate some process, okay, the motivation is what I was saying before. The fact that now I get completely, I couldn't get the plus, okay, so if I look for this process, if I could select this process in a scattering, okay, at the LHC, plus helicities, okay, it will tell me it's not possible, okay, but wherever, I don't know, future colliders, it will be important. You have polarization, or you could have plus minus here. Okay, I know in the standard model this is 0, 3 level. Okay, so it only comes from, it will only come from higher dimension operators, okay? I don't calculate it to you, I can calculate it, okay? It will come some kinematics here, okay, that I don't know. Okay, so when I square the amplitude to get the physics, this will go with lambda 4. You see, it's important if I have interference or not. Okay, if I don't have interference, this goes like lambda 4. If I have interference with the standard model, because it is an expansion, I have 1 over lambda square terms. Okay, so there is a selection rule of when you have interference or not. Okay, because of this 0, I have interference. If I look now at a process that is different, I have many of these examples. Okay, but if I look at the minus, plus, now I can have in the standard model. So I have now a standard model plus 1 over lambda square. Okay, let me call it BSM. Okay, higher dimension operator. I like to call it BSM because it's not squaring. And now this goes like, of course, a standard model square leading, and now the subleading term, the small deviation that I want to look beyond the standard model goes like lambda square. A standard model, conjugate a BSM plus dot. Hermitian conjugate plus 1 over lambda 4. Okay, so it's important this helicity, these strange properties we have to explode these things. I don't know. There is some attempt to do these things, people try to do, but there is a potential thing that of this selection rule of helicities, okay? And let's see if in the second hour I can go to do loops, because Rodrigo already told you, okay, he was calculating all these dimensional analysis, and in the standard model, when you do it, you get many zeros that you don't understand. You get a calculation, it looks like there should not be 0. You do it, you sum all the Feynman diagrams, 0. Okay, no, each diagram is non-zero, 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 sum them, 0. Okay? And this will come, okay, one of them were explained, and I will try to explain them, have to do with these selection rules, okay? Has to do with the property that the standard model in all amplitudes except 1, lambda total is 0, okay? Related with this interference. pattern. See, we can do in the second hour, okay? But that would be the main goal. Try to explain these zeros, okay? This information from the on-shell amplitude, okay? Let's stop here. Yeah, you don't get anything because there is no square bracket, no angle bracket. Cannot, this I can change it. I have another one with plus plus, that is an obvious change. But here there is no more, yes, there is no. Here? Here I can, you see symmetric, as you can see. Sorry, okay, but you see, I went too fast, and thank you. And this is, doesn't make sense. Yeah, this is not two lines like this. Where I wrote it, okay. Thank you. 1, 2, 3, 4, minus, minus, plus, plus. Yeah. But I said, this is at the level of your grandmother, okay? You just put here squares and brackets with numbers, okay? They cannot be repeating because inside we know what it is. This is a contraction with an epsilon, has to be, that isn't symmetric, so the indices have to be different. You just expand, okay? I mean, it cannot take you more than 5 minutes to start, okay, doing this, okay? The difficult part will be, if you didn't understand the rule of the little group, is to understand this as a function of what exchange of particles, what is the helicity you are exchanging there. But that you can write this, yes, okay? Has to be dimension, it's a 4-point, dimension 0, okay? So I have to 2. See, in some sense, I can tell you I forgot some. I can have this square. I can have, you can see what if I miss one. No, because you can have this square, I have it here, no? The two angles, I can have one angle and one square. I can have two squares, that is the equivalent of putting plus plus here, the trivial one I don't put. You see, it was relatively easy, you see all the things. And each of them I started to tell you, I can tell you if you are interested, I have it here, but I don't know, I don't want to give you too much information. Each of them is related with some dimension 6 operator that you have in the standard model. Okay, you know there are 59 or whatever, I don't know how to count them, many of them, okay? Of course, I don't put the flavor. It will be also more when I start putting flavor here because we have electrons, quarks here, okay? So when I start putting flavor, I have to be writing here the invariant tensor, and there how to put the AI. If I put AIG, KA, I have to tell you what is how I pack here the indices, the flavor indices, okay? I have to write an invariant tensor because I have the symmetry. I have to have the symmetry, okay? But it's relatively simple to see that you are not missing anything, okay? Okay.